Alright, so this is the lecture on 4.1, which is rates and unit rates. Okay, and this whole chapter deals with rates, unit rates, ratios, proportions, and percentages. So unlike the last two chapters, this chapter and these four sections that make up this chapter are going to be just obviously applicable to the real world. In fact, every single problem that I'm going to look at for this lecture at least is going to be a real world problem. So it's, the previous two chapters on set theory and logic, they're still definitely applicable to the real world, but it's a bit of a stretch, maybe. Though the truth tables, that if you're doing anything like, let's see, one example I can think of is if you want to get into law and get a law degree, and you have to take the LSAT. Having those skills to know how logic works and how to build truth tables will really help you there. I've looked a little bit at some of the questions on the LSAT, and a lot of those would be easily solvable with techniques that we learned in Chapter 3. But this will not be a stretch to say that it's applicable to the real world, because rates and unit rates and proportions and percentages exist just everywhere in the real world. So first, let's get a definition down here for what a rate is. And a rate is just a fraction, but the thing that makes it different from just a fraction of two numbers is that it compares two measured quantities. So a rate is a fraction comparing two measured quantities. So I list a couple examples in the notes here, like, for example, 110 miles per 5 gallons. This is just some arbitrary example of a rate. You see how 110 over 5 would just be a regular fraction, right? But when I attach units to the back of it, so now it's not just a fraction comparing 110 and 5, it's a fraction comparing two things that have been measured, right? Two things that have been measured, specifically 110 miles compared to 5 gallons. And of course that can be reduced, and we're going to look at that later, but we're just getting an idea for what a rate is. Another common rate you'll see all the time is dollar amounts per some quantity of weight or volume for some item that you're buying. Okay, and how does this differ from a ratio? Well, a ratio is pretty much like, a ratio is just a special kind of rate where the measured quantities are like the same, or they're like in the same category. Like an example of a ratio would be in a room full of people, there are, maybe 10 men for every 10 men to 12 girls, or 10 men per 12 girls, or something like that, or women, whatever. So a ratio is a rate. It's just a special kind of rate where the things you're comparing the units are typically like related. They're like in the same category. Whereas a rate, in general, the units don't have to be related at all, right? Like, for instance, miles is a measurement of distance, and gallons is a measurement of volume, and dollars, American dollars, is a measurement of currency, and ounces is a measurement of weight, of mass, or volume, depending on if it's fluid ounces, right? But so they're not related, and by comparing the two different units, we're getting a new idea for like how these numbers are related. So that's what a rate is. All right. let's just get straight into some examples. I'm looking at example 1 here. Okay, 1 second. Okay. So example 1, I'm not going to write it all out because it's written down in the notes for section 4.1. I'll read it to you though. It says, you are comparing the prices of 2 bags of apples. The first bag is $6.99 for a dozen, and the second bag is $3.59 for 5 apples. Write these as rates. Okay, so the first instruction is just to get those two numbers written as rates, and then to determine which is the better deal. So first, let's get these written as rates. Anytime you're dealing with money, the money's going to go on top. So the first bag is $6.99 per 12, and we don't just want to say 12, right? Because a rate has to measure, or is a fraction comparing not just numbers, but two measured quantities, meaning we have to write the units here. So I have to say apples. So it's $6.99 for 12, for a dozen, which is 12. And the other one was, what was it? $3.59 for 5 apples. So you see both of these numbers have the unit attached to them. Of course, for dollars, you know, for currency, for our currency, we write the dollar sign up front. It's pretty much like the only unit that you'll do that with. Most units are typically written behind the number, but, you know, this is how we write a dollar amount, with the dollar sign up front. Okay, so we got them written down. That's the first part. Now it says, which is the better deal? Well, we can't directly compare these because they're measuring a different number of apples, right? Like if this was $3.59 for a dozen apples, then it would be clear that this was the better deal. But the thing is, the money's lower, right here, but also the number of apples is lower. And if you've done, you know, shopping in the real world, you probably have a feeling that this is going to be the better buy, because typically when you buy things in bulk, it tends to be cheaper overall, right? That's why Sam's Club exists, right? You know, and other places where you can buy bulk, because it's cheaper to buy bulk. Now, of course, then you get into the question of, you know, if you're just buying for yourself, are you actually going to eat 12 apples before they go bad? You know. Anyways, let's actually get these to see if we can find out which is the better deal. So how do you compare fractions, right? So this is boiling down to a fraction comparison problem. You know, given two fractions, you want to know is this one greater or is this one greater? And the way to do that is to get a common denominator, right? So in previous math classes, you might be expected to know, like, oh, how do you compare 1/2 and 1/3? You get a common denominator of 6, and then you can say, okay, so the 1/2 was bigger. But here, it's going to be even easier, because instead of taking the denominators and bringing them both up to like whatever the common denominator for 12 and 5 would be, instead of doing that, all we do is bring them both down to 1. We force them both down to 1. So in the end, our denominators are going to look like this. And the question is, how do we get the numerators now? And the answer is, all you do is you just divide. You just do 6.99 divided by 12. And that's going to force it into some new rate of some dollar amount per 1 apple. So if it's $6.99 for 12, then how much is it for 1? Well, you just divide. And of course, now is going to be the time that a calculator is going to be useful, because not only do you guys not want to probably, divide this by hand, I also just don't feel like teaching it, right? So if we can all be on the same page and just say, okay, we don't need to know how to divide decimals because we all have calculators, and I'm getting 0.5825, okay? Now, of course, money, or at least American money, only goes out to the 100th place, so I'm going to be rounding that, but let me go ahead and get the other one as well by doing 3.59 divided by 5. And this is giving me 0.718. Okay, so now clearly this one's more expensive, but before we say for sure, let's just round our answers to the appropriate decimal point since we're dealing with currency, US currency. So it's going to be 0.58 per one apple, or you could just say per apple here since it's, one apple. And then over here it'll be 0.72 rounding up here per one apple. So clearly that one is more expensive, so this is the better buy. The one on the left, the $6.99, is the better buy. $6.99 for 12. Because it's cheaper per apple. It's cheaper per apple. Okay. The numbers that we just found, or rather the rates that we just found, are called unit rates. So-called unit rates because in math, unit means one. Unit means one. Like if you remember, if you've ever taken trigonometry and you learned about the unit circle, it was a circle of radius 1, and unit is, it just means one all over the place in math. So it's unit rate means a rate with a denominator of 1. Of course, with whatever unit attached to it as well. So and unit here meaning two different things, right? Unit rate in the context of this is it means 1, and these also, all these measurements are units, like dollars and apples. Okay, so it's a rate with a denominator of 1. One item, one apple, 1 ounce, 1 gallon, so whatever the measurement is. Okay, and they let us, why are unit rates so useful? They let us compare prices directly, and other things, not just prices, but in particular, one of the most useful places that you'll for unit rates is comparing prices. And if we really want to be specific, when we're dealing with money, we can call it a unit price. But it's okay. Unit rate is just the more broad term. If you're dealing with money, if you'd like to be more specific, you can call it a unit price. And if you ever shop at Walmart, which of course, we all do, the way that they write their price tags, they'll have like whatever the price is for the, so for instance, compare, this apple thing, bag of apples, 5 apples, it would say $3.59, and up in the corner there's going to be a little box that tells you that it's, whatever its unit price is. So if you've ever seen a price tag from Walmart, it's going to have I think it's like a little orange sticker in the top left or top right, I can't remember, that tells you what the unit price is. So at Walmart, you don't have to do the math. You can just look at the stickers. And of course, their motivation for doing that is not that they're trying to be nice. I think it's just that, they sell that great value brand, which is always cheaper per, it's always a cheaper unit price, and they want people to be able to see that directly. All right. Alright, let's talk some more about how unit rates or unit prices can be useful. So I'm looking at, it would be helpful too if you look at the notes, I give a few other examples of unit rates that are not money. I write 22 miles per gallon or 22 mpg. Of course, that's a unit rate. Or a speed, mile per hour. So let me actually write that down. Note that typically speed is given as a unit rate. For instance, if I ask you how fast you're going on a highway, you would say 60 miles per hour, right? You would say 60 mph, which this is just our way of saying miles per hour. So this is, the little p means per, and it literally is replacing the fraction bar. So this is the same as saying 60 miles per 1 hour. Right? You never give your speed as like, oh, I was going 240 miles per 4 hours, right? Because no one talks like that, right? You know, if you're talking about a speed, you're going to give a unit rate. Or if you don't have a unit rate, you're going to, figure out what the unit rate is before you tell anyone what your speed was. I want to make another note here just about the units. This isn't really, this isn't part of like necessarily like any problems we're going to do. Since we're not going to deal with the metric system too much, but if you're going into any science, like, and you need chemistry or anything like that, you should just know that typically when you abbreviate miles, you abbreviate it as MI, because M is, the letter M is used for meters, which makes this little MPH thing a little bit misleading, but since we use MPH so much in America, we all just know it means miles per hour. But in general, a lowercase m by itself typically stands for meters, not miles. And if you want to be really technically correct and make sure everyone knows what you're talking about, and you want to abbreviate miles, you should abbreviate it as MI. Alright. So let's get into another example where unit rates can be useful. Just another way of using them. Example 2, which I think in my notes I just forgot to label the number of examples. Or I forgot to enumerate my examples, but it's okay. So suppose tortilla chips cost 36.5 cents per ounce. So I'm given a unit rate here, or unit price, 36.5 cents per 1 ounce. And this is potato chip or tortilla chips. They cost 36.5 cents per ounce. If a bag costs $4.75, so the total cost for a bag is $4.75. And what's the question going to be? The question is, how many ounces are in the bag? How many ounces are in the bag? And then we're told to round our answer to the nearest hundredth. Okay, so we have a rate, a unit price, and we have the total, and we want to know how many ounces are in the bag. So, first thing we need to do, hopefully you notice, that these are in two different measurements of currency here. Right, so let's get this measured in dollars. Okay, so let's say this is the same as $0.365 per ounce. Right, that's what 36.5 cents is. It's $0.365, right? To get back and forth between cents and dollars, you just divide or multiply by 100, which effectively scoots the decimal point twice that way or twice that way. Depending on which direction you're switching to. Okay, so now we've got both measured in dollars here, well, at least the unit price measured in dollars per ounce and the total measured in dollars. So what we've got is we've got some bag that in total costs $4.75, and we want to figure out how many ounces it is, and we have the unit price of dollars per ounces. So what we're trying to figure out is how many times 0.365 fits into 475, because each one of these is going to represent an ounce, right? Each one of these little times that this fits into that is going to be an ounce. And we could take 475 and continuously subtract this from it and then keep a tally of how many times we subtract, but we are more savvy than that, and we know that repeated subtraction, keeping track of repeated subtraction, is the same as division. So long story short, we're going to take the total amount divided by the unit price, and that will give us the quantity of the number of ounces in this bag. So we're going to say 4.75 divided by 0.365 over ounces, over 1 ounce, which effectively is just going to be 4.75, plugged into the calculator, 4.75 divided by 0.365, whoops, which gives me 13.01369, etc., 86, and this is measured in ounces, and I'm told to round it to, what, the 100th place? Yes, to the 100th place. So I look at the 100th place, and it's a 1, look to the right of it, that's a 3, so I just round down by chopping all these off, so I get 13.01 ounces. So 13 ounces, really, if we were gonna, I mean, that's super close to 13 ounces. Okay. Okay. Now, I'm gonna go on a little tangent here about what's going on with the units here, with the units. Okay, and I'm gonna go on a tangent about dimensional analysis. Okay. If you are getting into any field where you're going to be measuring things, so forensic science or chemistry or business, whatever it is, if you're going to be measuring things, then dimensional analysis is going to just save your life. It's the most useful technique for converting units and doing multiplication and division with things that have units attached. So what's going on here with this little division, and how did I end up with ounces? So I've got 4.75 divided by some fraction, which is measured in dollars. Now you've probably learned dimensional analysis before if you've ever done any like measurement stuff and like looked at how to convert between units, like inches to feet and all that. You've probably done that before. Okay, so now recall to divide fractions, you multiply by the reciprocal of the second fraction. Okay, and now what's happening to the units? Well, they cancel just like a factor would. So dollars cancels with dollars because now they're, one's in the top and one's in the bottom. And I just end up with 4.75 times 1 ounce, so that's going to be 4.75 over in the bottom. Now remember, technically this is over 1, right? So in the bottom I get 1 times this 0.365, and the unit, the only unit that's left is ounces. And then all that remains is to actually calculate this division, which we already did, and we got the 13.01. So that's how I ended up with the unit of ounces there. Alright. Okay, so now let's do example 3, which is very similar to example 2 in that we are given the unit price to start off with, which is 24.5 cents per ounce. 24.5 cents per ounce. And you can write the 1 in front of the ounce, or you can just write ounce, OZ for ounce. It's just up to you. Just remember that when you read this, you would say 24.5 cents per ounce or 24.5 cents per 1 ounce. Alright. And what would a bag of chips cost if it contained 18 ounces? Round your answer to the nearest cent if necessary. Okay, so we've got an 18-ounce bag. Now this should be more intuitive to you. If it's 24.5 cents per ounce and you've got 18 ounces, how do you find what the total cost would be? You multiply, right? You multiply these two numbers, and actually you can see with the dimensional analysis, if I was to point that out here, ounces and ounces would cancel when you multiply, and you would only be left with cents, which is what we want, right? And in the end, we're going to convert the cents to dollars. Well, how about we do that at the end? So we're going to have 24.5 cents per ounce times 18 over 1 ounces. The unit ounces cancels, so we're going to be left with some number of cents, and let's go ask the calculator what 18 times 24.5 is, and it says 441. And then as a dollar amount, that's going to be $4.41. And it says to round to the nearest cent, but we're good, right? We had no decimal part to our cents, so no need to round here. All right, let's talk about one of the most useful techniques that comes from math with fractions, which is solving proportions. Okay, proportion's easy. It's just or at least its definition is, a proportional equation is just two equal rates. They don't even have to be rates, it's two equal fractions, but in particular we're dealing with rates. So we're going to say two equal rates. And typically where proportions are useful is when the two fractions are rates. But an example of a proportion that's not a rate, where neither of the fractions is necessarily a rate because there's no measurements attached, is this: 1/2 is equal to 3/6. That's a proportional equation. Now, of course, we're going to be looking at things with units attached. So one that we found earlier was that, what was it? $6.99 per 12 apples. That was equivalent to its unit price of 58 cents, or $0.58 per one apple. And of course there was the other one too, with the $3.59 per 5 being 72 cents per one apple. That would be another example of a proportional equation. Now, proportions are useful when you've got some rate, some known rate, and you may want to scale it up or down. So say I know that it's $6.99 for 12 apples, so I want to know, well, how much is it going to be for 48 apples? And then I would say, okay, well, I'm scaling the bottom up by 4, so I should do that to the top as well. And there's different ways to think about solving a proportion, but that's how a proportion can be useful. You're given a rate, a relationship between two quantities that you know about, and then you're asked to find a proportion to it, or a rate that's proportional to it. So a great example of that is like scaling a recipe up or down. So let's look at example 4. Which says you're baking with a recipe that calls for 2 cups of flour, 1 2/3 cups of butter. Let me write these down. So I'll say 2C for cups of flour, 1 2/3 cups butter. Where are we? Okay, so say you're making cookies or something, and you've got this recipe that calls for 2 cups of flour for every 1 2/3 cups of butter, among other things, right? But we're just focusing on these two for now. And you have 3.5 cups of flour, but you want to use it all up. So you have, because let's say this is some recipe that you make, and it's pretty much the only thing you ever bake, so you're never going to use the the flour for anything else, and you don't feel like going out and buying more right now, so, and this recipe calls for 2 cups, and you don't quite have enough to double it, so your question is, I just want to use up my flour, so how much butter do you need? And you're looking at your butter and you're trying to decide, okay, how much butter do I need? Because if I don't have enough to do this, I don't want to have to go to the store. So I'm just trying to figure out how much butter you're going to need. Okay. And of course you want to keep the ratio of flour to butter the same, because you don't want to mess up your recipe. right? So what we've got here is we've got a known ratio, or maybe I should say rate, a known rate of 2 cups of flour for every 1 2/3 cups of butter. And I want this rate to stay the same, so equal to a new rate where I'm going to scale up from the 2 to make it 3.5 cups of flour. And I want to know how much cups of butter here I'm going to need. And it's not quite easy to see what the 2 got scaled up by to be a 3.5, right? And you don't just add, right? You know, if you don't just say, okay, an extra 1.5 cups of butter because that's how much I added here. No, because that's not how ratios work, right? You don't keep a ratio or a rate the same by adding something to the top and bottom. That's just not how fractions work, right? You have to multiply by something in the top and bottom. And what did I multiply by to get from 2 to 3.5? Well, that's not quite as clear, right? So the routine way of solving a proportion like this is to cross multiply and to set the 2 products equal to each other. So the first product will be 2 times x, and at this point you're going to want to drop the units. So you're going to have 2 times x. The units are still there, and they will work out in the end, but it's just save yourself some work. You don't really need to carry them around. Just make sure you have your units at the very end, that whatever the appropriate unit is for the problem you're solving. So I've got this product, and I'm going to have it equal to 1 2/3 times 3.5. And this whole cross-multiplying thing, it's nothing fancy. All we're doing is we're multiplying by each denominator on both sides. So I'm multiplying by x over here to get it to cancel, which means I need to multiply by x over here. So now there's an x up here. And then I'm multiplying by 1 2/3 to get it to cancel, and that would mean a 1 2/3 ends up over here. So those 2 steps at once gets you right here. That's all the cross-multiplying thing is. Okay, so now clearly I'm going to need to do some fraction multiplication here, which, remember, just make them improper and then multiply straight across. Okay, I'm going to work on this piece of paper. Okay, so I'm going to have 2x is equal to, let's see, 1 times 3 is 3 plus 2, so that's going to be 5 over 3, and then this will be 7 over 2. No common, nothing nice that can cancel here, so I'm going to just go ahead and multiply straight across. And now I'm going to divide by 2 on both sides. Or I could say, if it makes you feel better, I'm going to multiply by 1/2 on both sides, because that's going to be easier to deal with over here with this fraction. And that effectively, multiplying by 1/2 cancels the 2 here. So I've isolated x, and I'm going to have 35 over 12. Okay, multiplying here. Alright, now writing it as a mixed number, I'm going to have nearly 3 cups, right? Because 36 over 12 is 3, but not quite. It's going to be 2 11/12, and this is when you should write your unit. 2 11/12 cups of butter. So that's the answer to this question. How much butter do you need? You basically almost need 3 cups, right? Very close to 3 cups. 2 11/12. Now, in the real world, you would kind of be in trouble here, because most measuring cups don't go to the 12th place, right? The smallest they go is maybe a quarter, maybe a sixth if you have that. So you would have to do a little bit of estimating here. You'd probably want to try maybe to convert these cups to tablespoons. And usually, if you do a recipe like a baking recipe, the butter's gonna be measured in tablespoons, anyways, not cups. But if you were to convert this to tablespoons, you might have an easier time dealing with that than trying to estimate. What I would probably do is just get 3 cups of butter and then take out like a spoonful or something and just call that 2 11/12. But maybe that's why I'm not good at baking. Alright, let's look at this final example, another proportion problem, and see how I have not done any just math problems for the sake of math problems in this section, right? They've all been real world stuff. I've not told you what a fraction or what a proportion is and then just given you something like this, you know, and asked you to solve for x or anything like that, right? I haven't done anything like that, just math for the sake of it, because all of these problems can slip into the real world so easily. Okay, example 5 from the notes says you're making dessert, but your recipe needs adjustment. Your oatmeal cookie recipe makes 4 dozen cookies, but you only need 3 dozen. If the recipe requires, okay, and then we've got a list of things. How much of the ingredients are necessary for 3 dozen cookies? Okay, so let's get this down. 4 dozen calls for 1 1/3 cups of butter, 2 teaspoons baking powder, and 1 2/3 cups of raisins. Gross. And probably other things, right? But because you can't just make cookies out of butter and raisins and baking powder. But I guess we're ignoring the flour and eggs and whatever else you need. That's another thing that's hard to deal with if you're scaling recipes up and down is eggs, because you can't really take half of an egg or anything like that. I mean, I guess you can, but okay. So we want to make 3 dozen cookies. So we're going to have 3 different proportions here. We're going to need to scale each of these down by something. And we need to decide how to set up our proportions. Okay, the way you're going to do it is you're going to say your first proportion, so the butter proportion, is going to be 4 dozen cookies. Calls for 1 1/3 cups of butter. That should be the same rate for 3 dozen cookies, right? We want to scale this down in some unknown cups of butter. And we could call it x. Okay, now I'm going to move through this calculation kind of quick here. So 4 times x, 4x is equal to 3 1/3, which will be 4. Well, yeah, it's going to be 4. You know what, I was going to work it out, but you should practice that. If you're not sure how to take the product of these two, then make sure you're brushing up on that fraction arithmetic. So 3 times 1 1/3 is going to be 4. And then clearly x has to be 1 here. So 1 cup of butter. Okay, now you're going to have to do that 2 more times, but the proportions are going to be similar. So it's going to be 4 dozen cookies. 4 dozen cookies for 2 teaspoons, I'll say BP for baking powder, equivalent to 3 dozen cookies. And you see, I'm gonna have the exact same numerators set up here, and some x teaspoons of baking powder. I'll cross multiply. I'll get 4x is equal to 6. Now, something I want you to notice is in all these proportions I'm setting up, the units are matching going straight across, right? So if you have a question, maybe you even had it earlier on, well, can I write it as like 2 teaspoons baking powder over 4 dozen cookies? The answer is yes, but your fraction over here better flip as well. The units need to match straight across. Alright, so now I've got this. So see, I've dropped the units here. Okay. No, that's not 2/3. Sorry. It's 3/2. Yeah. 3/2 or 1.5 teaspoons of baking powder. Okay, and the last one is those nasty raisins. So 4 dozen cookies per 1 2/3 cups of raisins, equivalent to 3 dozen cookies per X number of raisins, or X cups of raisins. Okay, so we're going to have 4X again, equivalent to 3 times 1 2/3. Let's see, that'll be 5. And X is going to be 5 over 4, which is 1 1/4, and this is cups of raisins. So you see how all of these quantities went down, right? They went down a little bit. So we went from 1 1/3 cups of butter to 1 cup of butter, 2 teaspoons of baking powder to 1.5 teaspoons, 1 2/3 cups raisins to 1 1/4 cup raisins. And all of these are very reasonable measurements, right? Not like that 2 11/12 we got a minute ago. So that's it for this unit. We got some homework problems to mark for review. I'll write them down here for you. 3, 9, 11, 12, and 21. Alright. That's it.